with any luck, I left you guys on Friday. We did the full example of vertex form, and we kind of walked our way through the start of an intercept form problem. So real quick, let's just take a minute to make sure that we did the, what do you call it, the intercept form one okay, without too much of a hassle. So remember I kept talking about over and over again the differences between zeros and terms? Thanks, Shimke. Air 5 for you today. You and I are getting along today. Tomorrow, it's over. Oop, that didn't work. There you go. So what happens here is if you've got intercepts, your x-intercepts are always going to be the zeros of the function, different from the zeros of the term. So if your zeros are at -2 and 2, that means that your terms would have been x plus 2, x minus 2. So this is getting you to write it out, the equation into what's the intercept form. So there's going to be an a here and a y. So the reason that they give you that extra point is so that you can substitute in to solve for a again, just like you did with the vertex form stuff. So there's a lot of the kind of the same thing over and over and over again. So what's -4 and 2? -2. -4 minus 2 would be what? -6. That gets me 12, I believe. So that gives me 8. 12a. Divide that out, we get, what would that be, 2/3? So your a value is 2/3. Don't use 0.6 with a borrowed rate. So your final answer would have been y equals 2/3 x minus 2 x plus 2. Now, what's nice is that with these problems, did you know that you could have checked any single one of them to see if you were right? How? Use your calculator. Yes, sir. For most of these problems, you can easily go to your calculator. And what I would do is go to my y equals, because what we're doing is we're creating a quadratic. Yes, sir. No, you just have to write it in whatever form they give. If they're giving it to you in terms of zeros, leave it in that form. Did you put them all in vertex? Ooh. So you completed the square a lot, didn't you? You got really good at it. Congratulations. Good work. Yeah, no, and this is a good mistake, but it's not really a mistake. On the test itself, I'll ask you guys, write the equation into vertex form, write the equation into standard form, write the equation into intercept form. And that's all you have to do. You don't have to go any further with it. There is validity to moving things back and around into different forms, but more often than not, if you've got a calculator and if you know how to manipulate the equations, that's my big thing, is trying to get you guys to understand, hey, that value of x is constant on the axis of symmetry. So you're able to work with it, not have to worry about changing forms. So what I would do is go back to my calculator and I substitute in that equation we just came up with. 2/3. So I'm doing alpha y equals to make a fraction. 2/3. Then my terms were x minus 2 and x plus 2, thank you. And then what I would do is just go directly to my table. I don't care what it looks like, but all I need to know is that this graph goes through that ordered pair that I used to substitute in. It was 8 and -4, I believe. Was it -4 and 8? Yes. So I would scroll and see if at -4 it equals 8. By doing that, I'm able to verify that that equation at least goes through that ordered pair. And it's a very helpful little trick. Okay? Are there any other questions with that intercept stuff at all? Are we okay on those? Okay. Let's add one more form. Let's add in the next form real quick. The next form deals with the sequence here. The next form is standard form. that, right? We're getting there. So let's walk through an example when you have standard form. Remember, standard form is your ax squared bx plus c, and I wrote it as equals y. I put it on the other side for right now because it's going to be easier to see how things drop together. Dinner's ready. So we have three sets of ordered pairs here. We have -1 and 5, 0 and 3, 3 and 9. And I'm going to write the equation then into standard form, ax squared bx plus c. Now, if you think about this, this format gives you x and y values trace times. That means 3. C. Manja. Anyway, so here's what it happens. You get this. -1 squared a plus -1 b plus c equals 5. What I'm doing is I'm substituting those values in. I'm going to do that for all three of the equations. I do it again. I have 0 squared a plus 0 b plus c is 3. 3 squared a plus 3b plus, I'm moving out of the way. It's 9. What I'm doing here is you're just directly substituting in values for x and y. Because I know what x and y is 3 separate times. You okay with that? Now I'm going to simplify that out a little bit. What's -1 squared? 1. Okay. So I'm going to simplify that out. Let's put it over here. So I get 1a minus b plus c is 5. I do it again. 0 plus 0 plus c is 3. So what's c? 3. 3. Okay, pretty easy. 3 squared is 9a plus 3b plus c is 9. So what started out to look really, really bad is only kind of bad now. Because remember when we talked about this before, whenever you have standard form of an equation, the c value was always what on the graph? Y-intercept, good. So I know that the y-intercept here is going to be 3. I know that. I don't know which way it's going, up or down right now, but at least I know it's going to go through 3 for the y-intercept. Okay? Now, here's what happens. Let me scroll this down here. Actually, move this off. What I'm going to do now is that since I know what my value of c is, I'm going to substitute it into the two other equations. Okay? In doing so, I get a minus b plus 3 is 5. 9a plus 3b plus 3 is 9. Which means I can simplify it one step further and get a minus b is 2. 9a plus 3b is 6. And now you're at a generic 2x2 system of equations, which happens to be one of the quickest ones to solve because on your second equation, what can you do real quick? I can take a GCF out of it. What's the GCF of that second equation? 3. If I take out a 3, does that 3 have any bearing upon the problem anymore? No. So I can do this. Let me move this off to the side. I get a minus b is 2. And then if I divide out by 3, I'm going to get 3a plus b is 2. How do you solve that system? You add them together. Very good. Remember that? We're using what's called elimination in this case. Since I have the same coefficient with opposite signs, negative 1 and 1, if I add those two together, it goes away. So I get 4a is 4, which means a is 1. So if a is 1, 1 minus what is 2? Negative 1. Very good. So it gives me a b value of negative 1, and we already had our c value of 3. Which goes back to the idea of standard form, ax squared bx plus c. Well, we have ax squared plus bx plus c. We have 1x squared minus 1x plus 3. And there's my equation. And it goes back to the idea I was showing you a second ago, checking it. If I throw that into my equation, or in my y equals part, in my table, I should get all 3 of those ordered pairs as parts of the equation. Yes, ma'am? Yeah. And you don't have to put the 1 there. It just so happens you can write it as x squared minus x plus 3. It works the same way. I'm just writing it so that we remember to see that your a value is 1, b value is negative 1, and c value is 3. So when you do that, if you go back to the equation, your y equals, let's see, clear that, I get x squared minus x plus 3. If I look at my table right away, I should come across those 3 ordered pairs. One of them was 0, 3. I forgot what the other ones were. Negative 1 and 5. Hey, that's a good deal. And the other one was what? 3. Hey! We math. Okay? We math. So it's a little weird, but by working your way through it, it winds up being kind of an ugly system of equation. Huh. I'm sorry, what's that? Yes. But you still had to figure out what A and B were. Right, that's what we did. But that's what we did. I see where you're getting with that. You just basically want to go ahead and skip a couple of steps. And that's fine. You recognize that you've got a y intercept and go for it. By all means. But what happens if you don't? Then you have to math. And the way that we did that is how you would math it. Okay? Let me show you an example. Our final answer here was that was the equation in standard form. That would have been it. That the 1x squared minus 1x plus 3. Yes,
So are all of these going to be binary that or is it going to be sometimes
I don't know. Maybe. Maybe. I don't know. Let's see which one was it. It was up here. Okay. Sorry, the order pairs are short anyway. So let's see. It's negative 2 and 0. Negative 1 and 2. 3 and 0. And I want to go to standard form. Okay. I'm going to go to standard form of this. Again, I'm going to start it the exact same way. I know what my zeros or my x's and y's are. This is the one reason why a lot of times they will put the y value on the other side. Because in terms of the ordered pairs, what comes first? The x values first. So that way you're not tempted to accidentally put the y, put your x value in for y. See what I'm saying? So it's one of those things when you're writing these things out in the standard form, it might not be a bad idea to throw the y value on the right-hand side. It's just kind of a play, because it doesn't matter where it is, but this way it kind of forces you not to make that silly mistake. So from here, I'm, again, going to start by substituting my values. I know that I'm going to get negative 2 quantity squared times a minus 2 b plus c And then 3 squared A plus 3, nope, yeah, 3B plus C is again 0. Are we okay with that? Now, do you have to do this initial step, or could you, in your head, square -2 and just write that out right away? It's fine. There's nothing wrong with that. This is only like the second time you've seen that, so I'm trying to show a little extra steps just to kind of so you remember what you're doing. Okay. So in this case here, move this over a bit. I'm going to get the simplified version, if you will, of 4a minus 2b plus c is 0. 1a minus 1b plus c is 2. 9. Sorry, I hate the fact that you give me 9s with my a's. And now you're in a system of equations where you have 3 variables and 3 equations. Okay. Where all the rules of simplifying, all the rules of elimination, that all still happens just the same. It's just a matter of what do you want to try to eliminate first. What a lot of times you look at is there a way to use one variable to eliminate 2 on the other equations? It gets really messy. Which means it gets to be very tedious. Which means we have to understand a little bit of something about math. For example, come back to this. How do I solve for x? Divide by 2. Why did you say division? You're solving for x, you have to you have to undo the multiplying, right? When you're undoing something, you're using what do we call that? You're saying it's a reciprocal. You have no eraser. Merry Christmas. So you're using the reciprocal on it because yes, the reciprocal of 2 is 1 over 2, but you're using what's called the inverse operation. You guys remember that? What's the inverse of addition is the inverse of squaring is square rooting, and so on and so on. Okay? So what you're doing is you're using the inverse operation by doing that. I think somebody said you're multiplied by a reciprocal 2, didn't you? What's the reciprocal of 2? It's 1/2 because the reciprocal, you're thinking of the slopes. Opposite reciprocal. This is the reciprocal is multiplied by 1/2, right? Remember what this meant? I think you just said it. Very good said. Right. Nope. No.
No, but that means oh, I think it's
No. There's a property. That means when you're dealing with exponents, it's an inverse property. It's a reciprocal. Okay? So 2 to the negative 1 is 1/2. Okay? Any exponent that's raised, any base value that's raised to a negative exponent is not happy. So it needs to move to the other side of the division symbol. So if it's in the numerator, that number has to move to the denominator. If it's in the denominator, it has to move to the numerator, vice versa. And it all works that way. This symbol can be found on a calculator. Really? I would not lie to you. So what I want you to do real quick is type in 2 to the negative 1. If I type in 2 to the negative 1, it's going to find the reciprocal, or it's going to use what's called the inverse. It's going to automatically, on this calculator, it's going to pump out 0.5. Do you remember how to change that back to a fraction real quick? Or you can do it quicker by just doing math and enter. You're right, though. There's nothing wrong with that. Math enter, we'll switch it back to a fraction. If it's a fractionable offense. Sometimes it won't be. Sometimes it'll just be a really god-awful decimal, but it won't actually be fractional. All right? So here's what happens. Going back to this. Going back to this piece here. What we can actually do is we can kind of undo all of this work at once in order to solve for everything. And the way that we do that is we use what's called a matrix. A matrix is a way of grouping data if it's read on the side of the chart. So what we use is what's called a matrix. What we're using is a coefficient matrix. Matrices are written by rows and columns. And depending upon which value it is, tells you how many rows and columns there are. Now, a lot of times students have a hard time remembering which one's which, whether it's a row or a column. Remember this, if you're going to row a boat, you're going to row left and right, aren't you? Because if you rowed a boat up and down, that means you went over a cliff and you are dead. No more rowing the boat. Do you know with that? So your rows go this way. Columns hold everything up. 3 columns, right? So what I'm going to do here is I'm going to take the coefficients of these 3 equations. My coefficients are 4, -2, and 1 going across. 1, -1, and 1. 9, 3, and 1. Now, what matrices do is that matrices are a way of gathering or collecting coefficients and working with systems of equations. It's another way to solve things. Guys, you know how we've done the elimination methods and substitutions? There's another way to just basically work with the coefficients themselves via a matrix to work and solve for what's called a identity matrix. It's kind of doing all the same work, but it winds up being a little bit quicker, especially for larger systems. But we don't have time to crank those things out by hand because there's a button. So what we're going to look at is this. We're going to take this coefficient matrix. We're going to take the inverse of it, multiply it. I'm sorry, before I take the inverse here. We're going to have these by their A, B's, and C's. Then it's going to have to equal, in our case, 0, 2, 0. So our problem is no longer to look like this giant, awful system equation. Our problem is going to look like this giant, awful matrix. Now, that matrix, that coefficient matrix, is being multiplied to a variable matrix. These are my variables. These are my solutions. So how do you undo multiplying again? Division, but in this case, we're going to use what's called the inverse operation. We're going to use the inverse button. So our answers here will become this A, B, and C, what we call a column matrix, because there's just one column, will equal our coefficient matrix, 4, -2, and 1, 1, -1, and 1, 9, 3, and 1, to the -1 power, times 0, 2, and 0. Again, there's a way to do this by hand, but it would take you about a sheet of paper. Exactly. All right. So what we do now is we use our calculator. In the calculator, you will notice that there's a button. If we hit alpha zoom, you get a matrix, and it comes up with the options for rows and columns. And what's nice is that if you screw up and you're not sure which one's which, if I type in 3 by 1 and I hit OK, alpha zoom, and then you might have to move it over left and right to get to it. Oops. So that's what a 3x1 matrix would look like. It'll tell me, hey, that's what that is. But anyway, we go back to do this again. We put this alpha zoom. I want to make a 3x3. So I get my shortcut key to come up. I already have the 3 there. Get to the right, hit enter. Scroll back down to OK. And now it comes up with a 0 matrix. Are we okay with that? Now, put in your coefficients. And granted, this is super easy to do, but it's super easy to press the wrong button. Make sure you're using the negative button for your negatives, not the minus symbol. What was it? 4, 2, 1? 4, negative 2, thank you. 4. Hit your right arrow always. Negative 2, 1. Right arrow. 1, negative 1, 1. And then it was 9, 3, 1, right? Thank you. So there's my matrix, my coefficient matrix. Put it to the negative 1 power just by pressing this button. And it's going to find the inverse of that. To that inverse, you're going to multiply it to its solution matrix, which was another alpha zoom. But now we have to make it a 3 rows, 1 column. And 0, 2, 0. Thank you. Press enter. There's A, B, and C. Now watch this. Math, enter, enter. It'll flip it back to a fraction. I prefer fraction. I know you'll get some crummy decimals, but a lot of times you get math, enter, enter, it'll spit out a nice clean fraction. Okay. So it is quite literally pressing a bunch of buttons. But you have to understand the right way to put the sequence in. And it's super easy to screw something up. So this gives me my solution matrix. So this is now my A, B, and C, which means my final equation would be y equals negative 1/2 x squared plus 1/2 x plus 3. And that's the equation in standard form that has those 3 points. Yes, ma'am?
I have a question. Why did the A go with 4, negative 1, B go with 1, negative 1, and C go with 9?
It goes sequential. Because what happens with matrices is, if we actually still did the whole matrice unit, what it does, what this calculation is doing as it multiplies through, is that it's figuring out what the identity matrix is going to be for that. The identity matrix gives you a 1, 1, 1 in the diagonals, and that means your first variable is that answer, your second variable is that answer, your third variable is that answer. So it just so happens that it's A, B, C, that means that's the A answer, B answer, C answer. Everything else is zeros. There's a whole slew of properties that have to happen. We don't do that anymore. Yeah, it's there! Woohoo! It's math magic. All right. If you switch them around, even if you put the one equation as a third equation, it'll still be ABC, and your values will still work out where it's negative 1/2 and 1/2 and 3. Yeah, no. It's this is the type of stuff that you can screw up and still be okay. Yes, ma'am. Yes, but you don't have a y-intercept. You can, but if I don't give you a count, then you're doing it because it's a y-intercept. Oh, one more. Yes, sir. I was just about to get to that. Now, I discussed this with first hour. If by chance I ask you to write the equation of the, what are these called? Parabola, or the, no, find the equation of this in standard form of the parabola, ax squared bx plus c. If I'm asking you to do that with no c value given, I would have to let you use the calculator because it takes way too long. But if I give you one that has a c value, you should be able to do the system equation without a problem. So if I give you one like this, where you don't have the c value, you don't have your y-intercept, I would allow you to use your calculator on that. Whereas if I give you one where this was 0, 4, then I would expect you to be able to do it without the calculator. Does that make sense?
So wait, this is not solvable.
What's that? 0, 4 would be your y-intercept, which would automatically make it the c value. So you don't have to solve for two equations. Yeah, because if you go the other way, if you go through with this one we did originally, that's the y-intercept, so you could have skipped most of this and gone right to here. And you can do a quick system equation with 2 by 2 without a big deal. Right? That would have been so bad. All right? So that's how that would have worked. So take a second, do that one. You guys got a bell? What's that? No, I wasn't playing. When you go through this, remember, a lot of times with this, you should be able to look at this knowing what you're trying to get to. Ax squared plus bx plus c is y. If you jump right to filling in the blanks of your matrix, that's fine. Okay? But it still would be a bad idea to at least write it out. And I know, I can guarantee right away, somebody's going to screw something up when we square a negative. -3 squared is -9 because my calculator said so. Yay! Because it happens all the time. Somebody's going to accidentally go too fast in the calculator because they think a 3 is a 2 and get the wrong answer. It's really simple to do this. And what stinks about this by using the calculator so much, it makes it too easy to make a dumb mistake. Okay? So just be cautious. Always double check what you're writing out before you do it. That way you don't screw something. Okay? Yeah, sometimes it's not bad. 6 in B's, that's good.
Yeah.
Oh, thank you. And that's what you'll screw up.
I messed it up.
And you get some really crummy numbers, didn't you?
No, I caught it.
Oh, okay. Because it'll still do the work for you. If you get a thing on there that says domain error, that means you put your column matrix in front of the inverse matrix. In order to make a multiplication work with matrices, this is a 3 by 3 times a 3 by 1. This is rows, and columns. The number of columns in the first has to equal the number of rows in the second, the way that it works. Otherwise, it doesn't. And there's a lot of, just be thankful we don't show you guys this anymore. It's just a lot of pain. a lot of handwriting. What'd you guys get for your solution matrix then? You got -1, -1, 5, -2? -1, 5, -2, which means your answer was -1x squared plus 5x minus 2. You got that? Again, you can go right back to the calculator. What's wrong? You go right back to the calculator with that. You can throw in the y to get it. And you can always double check it just by going into the table to see how it works out. Okay? For doing that one? Yeah. Now, going back, yes, ma'am. It's 5x. Let's use the coefficients. Yeah, it's -1x squared 5x squared. So the test itself, we have 5-1 through 5-8. I think we skipped 5-6. 5-6 was graphing systems of what? Then we skip 5-7. All right, then we skip 5-7. I think it was one of those. That one was solving or graphing inequalities of quadratics. You graph a quadratic and you shade on the positive or negative side like you would have any other line. Same basic principle, calculator, which means graphing calculator versus non-graphing calculator portion. A lot of the stuff that'll be on there, you can, if I can say factoring now that there's certain ways you can do that. With the graphing calculator, that means you won't be using the graphing calculator to do that. And then with the graphing calculator, you'll have for word problems and for if I give you one of these, what we just looked at for something along those lines. Excuse me. What I have tonight is just a bunch of first off some review stuff. It has 3 of these, sorry, not review, not 3 of these, but there's one of each style of the write the equations in it, as well as a bunch of junk from earlier in the section. Tomorrow, I plan on doing is going over a bunch of that. I do have a few more of like factoring style problems. I think for the most part, as I was looking through my notes and some of the stuff that I've already painted out to you, we've kind of done just about all the word problems that I've had, kind of like a little nest egg, if you will, of them. I think I might have like a couple here or there, but we'll try and rework a few of those. But remember, we spent time going over the quiz junk and trying to figure out what next was, so on. So that'll be on Wednesday, and then on Thursday we'll start up with conics, which basically we start with parabolas again, but all of a sudden you're going to know that parabolas can turn left and right. Yes, exactly. We're getting there. If you look on the good old-fashioned internet, I hear it's on computers. I don't know how many word problems there are. Oh, think there's 4. Maybe 3, I guess. So. Yes. Yeah. Oh, did I not put it down there? Oh, nuts, I didn't put it down. All right, I just put it down there. Yeah. You guys are silly. Do those, please. On page pi. Like your face. Yeah, I got to pause. I'll pop about there here in a second. I thought I typed it in a second already, did not. So, for those of them, give me a second. I'll pop them in there. All right. It's straightforward. What's that? Yeah, where it says 1 through 3, list the important stuff. Those are graphs. I don't want you to graph them. I want you to tell me where's the axis, is it symmetry, vertex, is it up or down, things like that. one, you have one new problem, there's one problem on here, I think it's the last one. That's like, are you paying attention?
I was having a flashlight.